So welcome. I forgot to start recording this, so I'll just quickly jump on it now. So basically, just remind ourselves of Maxwell's equations. We have basically the electrostatic version of Gauss's law, which is interesting because it's Q inside over epsilon naught. And then we have the electrostatic version. Then we have the magnetic version of Gauss's law, which is not so interesting because the flux lines start in a continuous loop, so we never get a value other than 0 for this integral. And then we have basically the kind of specialized version of Faraday's law. We said that EMF is equal to minus n d phi by dt. And we said, well, hold on, the EMF is equal to the line integral of E dot ds. And I can justify that by saying, well, my units for electric field will be newtons per coulomb, and my units for my distance, my loop, my little bit of length would be meters, and newtons times meters equals joules. So that goes down to joules per coulomb, which is a volt. So from a unit point of view, even if I can't remember where it comes from, I can justify it to myself. So this is a modified version of Faraday's law. And then we talked about Ampere's law, and we said, well, B dot ds was equal to mu naught times I. And then we said, yeah, but there's this problem with capacitors, so let's play with that. And we invented this thing called the displacement current, which we never pursued, because what it does, it just leads here. So we have these 4 equations, very familiar, but we didn't do much with, a little bit modified and a little bit modified. Okay. And then we started saying, well, let's remember Gauss, remember those Maxwell's equations. Now what about good old Hertz? Hertz basically was playing with, he was playing with electricity and induction and capacitance and the like, and he made up a system where he effectively made a transmitter by taking a coil and having it, energizing it using energizing it, and so he could get a spark across a gap, and that spark actually transmitted light, but it transmitted some other things as well. And when he put a similar receiver nearby, he actually could induce an EMF in this receiving coil, which would cause a spark. And so he reasoned there must be energy going from one to the other. So he's transmitting energy wireless. Like light does, the sun does that, but he's doing it in his own way, in an invisible kind of... He could have just lit a fire and photons would have gone. But he's got these invisible photons, if you like. Are they photons? What are they? All he knows is he creates a spark in the receiver. And then we said, well, okay, so if we take Maxwell's equations and we play with these, we can basically, and we pull it out of a hat, we say, well, solving for these 2 Maxwell's equations, which is basically Faraday's law and Ampere's law, we get this wave equation that comes out. And then we say, well, okay, that tells us that by analogy, we found before that 1 over v squared term is acting like a 1 over mu naught epsilon naught term in this wave equation. So that should be the speed of this wave, and they figured out what it was, and they found it was the speed of light, and they knew the speed of light by this stage. So they were like, oh, this stuff is just light, it's invisible light. So I need you to know a couple of things. I need you to know that the speed of light is equal to Emax divided by Bmax, and we just pointed out that Emax is the maximum vector for the electric field, and Bmax is the maximum vector for the magnetic field. And I just got to give you those numbers. Emax in newtons per coulomb, Bmax in Tesla, or I can ask you for 1. I can ask you for Bmax, and you know that C is 3 times 10 to the 8. So let's do a quick calculation. We say electromagnetic wave, and we say that Bmax is equal to 2 millitesla. And I know that C is equal to 3 times 10 to the 8. You should know that, meters per second. So I want to find out what my Emax is. What's the maximum electric field? And I go, C is equal to Emax over Bmax. So Emax is equal to C Bmax, which equals 3 times 10 to the 8 times 2 times 10 to the minus 3. I've got to be in Tesla, of course. So that's 6 times 10 to the 5 newtons per coulomb. And that's a really big field, frankly. That's a really big field. And that's because I got a really big magnetic field there as well. But that's how you do these. It's just remembering the equation. And then the next thing that I'd like you to think about is, so we have these electric field vectors and we have these magnetic field vectors, and they're playing off against each other. And we can think of them as creating, in a cross product, for example, we can think of them as creating a answer vector, and we call that answer vector the Poynting vector. Probably named after whoever came up with this, but I'm not sure. Poynting vector. And we can say, well, the Poynting vector is equal to 1 over mu naught E cross B. Again, no justification for this. And what we find is that our intensity, which is in watts per meter squared, intensity keeps coming up a lot now. So get comfortable with it. It's the power per area, watts per square meter. The intensity is equal to this average Poynting vector, which equals E max B max over 2 mu naught. And I would not bother about the rest of it. It's not that you're not responsible for it, but you can always work it out. So let's do this. So we say radiant energy from the sun comes as a plane wave, and the intensity is equal to 600 watts per meter square. And what is the peak value of the magnetic field? So I want B max. So here's the sun, and here's the waves coming down. And at this point here, I have my intensity. I want to know what the peak value of the magnetic field is. So I say, well, hold on. My intensity is equal to my Poynting vector, which equals E max, B max, over 2 mu naught. And it's like, there's 2 that I have problems remembering. Yeah? There's no epsilon naught in this, it's just 2 mu naught. And so then I remember, oh, but I also know that C is equal to E max over B max. And I want to find B max, so substitute for E in there. So I, which is equal to S, is equal to CB max. That's just rearranging that bottom equation, times B max over 2 mu naught. So and so now I want to find my B max. So B max squared is equal to 2 mu naught I over C. So B max is equal to the square root of 2 mu naught I over C, which equals 600 times 12, that's 1200 over 3 times 10 to the 8 times mu naught, and you're going to square it. And that would be Tesla. And you know, frankly, on a test, if you left it like that so I could see the bones, I'd probably go, that's fine. I say to you, don't leave me the square root, but that's when you got, you know, whole things you're supposed to calculate. But I'd kind of be all right. Cool. 2 things. Next thing, not so interested in the next thing. It's somewhat interesting, but it's just, I had to draw a line when I was doing the no equation sheet. You got to draw a line somewhere. So I just drew a line and said, I don't need this guy. So if you look back on the old test, you will see this questions on this somewhere. But that's because the equation sheet was there. Okay? So you don't have to remember this. So basically, it just brings up this issue about a photon has momentum but does not have mass. And I can't give you a good explanation for that. It comes out of relativity, I think. And I just, you know, it has momentum but not mass. Okay. So if I have an absorbing surface, then the photon comes like this. So that's minus p because it's going in the negative direction. But it never comes back. So force, which equals my change in momentum, is equal to minus p newtons. Yep. But if I have a reflective surface, then my momentum of my photon is reflected. So force, which equals my change in p, is equal to my final, which is minus p. I'm sorry, that should have been 0. There's nothing coming back. So it's 0 minus p. And I'm sorry, that's going in a positive direction. Sorry, I'm really, yeah. That is, let's do this again. It's 0 minus plus p. Getting my signs right, which equals minus p newtons. Whereas on this bottom, I have minus p minus plus p, which equals minus 2p newtons. So you get twice as much force on a white surface as you do on the black surface. So if I make a machine which basically is looking down from above is like an envelope of glass, and I have a cross on it, and I make it so that the black surface and the white surface are so I get this right. So if I look at it, I see, I'll show 2 of them. I see one of them has been black and the other one's been white, and I suspend it in a low vacuum. It will spin because it's pushing more on the white surface than it is on the black surface, and it spins. And you go to Moseley and you buy something that looks like this, and it spins. But it spins the wrong way. And it spins the wrong way because the ones at Moseley don't have a good enough vacuum. And the friction this is not a very big effect. So you can't just have a needle with this thing hanging on it. The friction will kill you. The ones in Moseley have a needle with this thing hanging on it because they have much bigger forces. Because what they're doing is, they basically, I'm just going to show the black side, I'm going to show the white side. What happens is the sunlight comes in, or the lamplight, and it heats this up because it's absorbing that energy, whereas on the white side it does not heat it up because it's reflecting the photon. You know, black clothes warmer than white clothes. So this black side is getting hotter, and because it's not a perfect vacuum in here, it heats up the partial pressure that's on the back side of this, and it expands, and so it pushes it forward. So the ones at Moseley expand, leaving the black surface behind. It's like the black surface is the motor pushing this thing around. Whereas the ones you can't buy at Moseley leaves the white surface behind because there's twice the momentum change. And these are called Crux radiometers, and the ones that really show this effect, I think, are called Landau, or I think it's Landau radiometers. They're very expensive and they're hard to make and all that kind of stuff. So yeah, the ones at Moseley show a sunlight effect, and they do, but it's the wrong way around. So you can calculate by looking at the momenta from an absorbing surface and a reflecting surface, and just playing with it, you can get the force or the pressure, if you like, out of it. And you get, for instance, the solar pressure is 5 times 10 to the minus 6 newtons per square meter. So if I have a reflective surface and I have a meter of it, I'll get 5 micro newtons out of it. which is 5 millionths of an apple's weight out of it, which is not going to drive this thing around and around and around, like in Mosaic. It has been used though on the Mariner. I think it was the Mariner space flight. So we don't give our space probes enough fuel to be able to kind of like set a course for Mars or Pluto and just drive there. We've really not. I mean, the problem we run into is that as we put more fuel in, the rocket gets heavier, and we need more fuel to get that heavier mass out of the Earth's gravitational field. So we end up with a no-win situation where, to put enough fuel in to climb to Mars. Mars is, as far as we're concerned, up in the air. Mars is further from the sun than we are. So if you imagine the solar system like a big funnel, and we're here, not quite as low as some of the other planets, but Mars is up there. So we do have to do work to get to Mars. Not just to get out of the Earth's gravitational pull, we've got to do that even if we go into Mercury. But once we're out of the Earth's gravitational pull, it's all downhill to Mercury. We go faster and faster and faster. To get to Mars, we not only have to get out of the Earth's gravitational pull, but then we have to go against the sun's gravitational pull to go out to Mars. It's hard. And if we tried to put all that in a rocket, all that fuel in a rocket to get there, we couldn't make it. The fuel density is not high enough. So they had this really smart idea. And what they said was, let's get the rocket out of the Earth's gravitational field and then drop it towards Mercury or Venus. And like a baseball bat hitting a baseball, we can have it falling, and rather than colliding with Mercury, the gravitational pull whips it around. But that collision, it's a kind of collision, that collision causes the speed of Mercury to slow down by an infinitesimal small amount, but gives a lot of energy to the Mariner space shot. So it's called the slingshot method. You drop down and you just pick up a whole bunch of energy. So when the things like the Voyager left the solar system, that's all from these huge collisions with these inner planets. It's really clever stuff. Really clever stuff. And it's based on the same principles as baseball, You're just not repelling it, you're attracting it round. But it's the same principles. So they were always short of fuel. They couldn't afford mistakes. If you ended up pointing in the wrong direction, that was a big deal. And they were in the wrong direction. They were just not pointing in the right direction for what they wanted. And I think they had a little bit of fuel because they wanted to slow down and go into orbit. So you need fuel to slow down once they got to Mars. But they didn't want to use it up on the way. So what they did was, somebody had this really bright idea about, if we have our two solar panels and they're both facing the sun because they want maximum electricity, if I just turn one of them so that it's on edge to the sun, I'll get this, 5 micronewtons per square meter. They've probably got about 3 square meters there, and it will just in time push around. And that's what they did. They steered the thing just ever so little using this solar pressure, which is kind of just a very nice, amazing little thing. Don't worry about this, there's no calculation for it. Final little bit. And I don't know if you've done this, I don't know if you did this in fundamental physics, but we kind of could just loosen up our whole idea about what light is and what light isn't. Your microwave basically shines a big light at your food. It just happens to be a different frequency, which is a different wavelength. It's in the microwave range. It's just a different kind of light. When you go to the dentist and you get an x-ray done, They're just shining more penetrating colours of light through your cheek. When you listen to the radio, this is a little bit harder. When you're listening to the radio, you're listening to modulated light beam that's redder than the reddest red that you can imagine. And all these colours are available to us. They're created in different ways. Usually temperature creates them. High temperatures give you bluer stuff. Lower temperatures give you redder stuff. We happen to have developed on a planet next to a 6,000 degree C sun, which tends to emit mainly, well, it emits red, orange, green, blue, indigo, violet. Mainly a lot of yellow. It looks like white when we look at it, but it's mainly yellow. And we developed eyes that are sensitive to those colours. We basically, on an evolutionary basis, said, we're going to give up on the night and hide, and we're going to be active and aggressive during the day. So that's why we ended up in caves, to stay out. It wasn't to keep out the sun. Well, in some areas it was, but, you know, it was often for protection. Other animals did not make that same choice. Bees have, I think it's ultraviolet. They can see better, and so when they look at a buttercup, they don't just see yellow. They see like all these lines pointing to where the stamen is, because the plant wants to be pollinated. So it's developed this pigmentation, which only the bees can see, or the bees can see anyway, and maybe others can see, but the bees can see. And so they go to, oh, look, there's something along this line. Boom. You know, we can't see that. There's a shrimp which has not 3 colour receptors, but something like 12 colour receptors. That's not like intense colours. That's colours we can't imagine feeding into its brain. So we made a lot of trade-offs. You know, if we had more infrared vision, I could follow somebody. Hunting at night would be a breeze. You'd see where all the animals are. You know, it's like, but we chose not to. But technology enables us to do that. And I remember being in a trade show in Tokyo, and there was a company opposite on the sales floor. There was a company opposite us, and they made infrared cameras. And the little party piece, most of these places want to get people in, so they have a party that, you know, little entertainment that takes place. And the party piece for this thing was, this guy would come out and he'd hold his hand up to the camera, and you see a picture of the hand that looked like a television image, but it was coloured, it was false coloured. It was temperature coloured, you know, they show us red was this and blue was that. And he would then take out a cigarette, light it and inhale it. And as the nicotine hit his system, his blood vessels would contract, his temperature of his hand would change, the colour on the hand would change completely. And you could even read out what the temperature of his palm of his hand was, and everybody would applaud. You know? The strangest thing, but that's just technology, incredibly useful. One final thing I'll leave you with is Richard of red, orange, green, blue, indigo, violet. What is the difference between blue, indigo, and violet? Well, yeah, but if I laid them side by side, could you tell me the difference between indigo and violet? Yeah. So my daughter was learning red, orange, green, blue, purple. And I was going berserk. I was like, this is part of, you know, for the sake of a colour? Why are you doing this? This is nonsense. And I thought, I'm going to show them. So I got the spectrum and I started carving it up. And it's hard to carve up because, you know, where does red end and orange begin? But, you know, you can get roughly a middle. And I'm thinking, well, it's 7 equal bits. And it's not. It's not 7 equal bits. Newton was the one who named these things. They're not 7 equal bits. It's kind of like he just put another colour in there just for the sake of it. And I started looking into why he put the colour in for the sake of it. And he did. And anybody, the reason why we have red, orange, green, blue, indigo, red, orange, green, blue, Richard of York gained battles, indigo, violet. Richard of York gained battles in, I'm missing one out, red, orange, green, blue. Yeah, you're missing out yellow, aren't I?
You said red, orange, green, so
Roy G. Biv. Yeah, I'm missing. Anyway, the reason why we have 7 as opposed to 6, which seems a bit more logical, is because Newton believed that 7 was a divine number. Just like the reason why Copernicus thought that the planets went in perfect circles was because he believed that nature used divine geometry. There's this sense of perfection in this universe that people keep wanting to impose on it, things that are special to us, and it doesn't have them. But you still got to know it's Richard of York gained battles in vain. Roy G. Biv, R-O, you know how to spell it. Red, orange, yellow, green, blue, indigo, violet. Okay, cool. And there we are. We have it. So let's stop there.